3.141519265358979323.
That's right! I'm here, standing on platform 3.14. The pie train is rolling into the station, full of delicious pies, and I'm here to celebrate Pie Day with you.
It's Pie Day. Delicious and sweet. It's the only number that you can eat. It's Pie Day. My favorite treat. Circumference divided by diameter d. It's Pie Day.
This year, I am going to look at a technique for estimating the number of pi with random numbers. This is a direct result of me rewatching one of my favorite internet videos from Stand Up Maths called Generating Pi from 1,000 Random Numbers. Now, in that video, Matt Parker, the host of Stand Up Maths, physically rolls dice picking 1,000 numbers to estimate the value of pi. I'm going to write some code. It'll probably take me actually longer than physically rolling dice, but that's what I'm going to do. However, I'm going to give myself a little restriction. I will not be using the random function in P5JS. No, rather, I'm going to pick random numbers from my favorite book, 1 Million Random Digits and with 100,000 normal deviates, and see how close can I get to the number pi from all of the digits in that book. So how does this all work? Let's say I pick two random integers, call them a and b. While in an ideal world, I would pick them between 1 and infinity, I need to establish some kind of range so that I can actually work with this stuff in code. I will choose the upper bound of 100,000 because in the random numbers book, the digits are grouped in groupings of 5. So between 0 and 99,999, I don't want to pick the number 0. You'll see why in a second. So my range will be between 1 and 100,000. The probability that these two numbers are co-prime is 6 divided by pi squared. Huh? Why is that? That's crazy. Well, this is one of the wonderful things about the number pi. It shows up all over the place in mathematics, and it's just delightful. If you want to understand a bit more about the derivation and proof of this number, this is where I would suggest you check out Matt Parker's video. He goes through this in detail. For me, in this video, what I want to focus on is this concept of co-prime. And how do I write some JavaScript code, or really in any programming language, to determine if two integers are co-prime? What does it mean for two numbers to be co-prime in the first place? Let's say I pick two numbers, 15 and 16. Well, for any number, I could list all of the factors of that number. What other integers that are smaller than that number divide into that number with a remainder of 0? With 15, I've got 5, 3, and 1. With 16, I've got 8, 4, 2, and 1. Looking at these two numbers, the only factor that they share is 1. If two numbers don't share any factors other than 1, they are co-prime. Another way to say co-prime is greatest common divisor. So the greatest common divisor of 15 and 16 is 1. That's the highest number that divides into both of them. Let's change the 16 now to 21. The factors of 21 are 7, 3, and 1. Oh, look at this! They share a greatest common divisor of 3. I should not be erasing this with my fingers. This means they are not co-prime, and in fact, Matt Parker calls this cofactor. So, if I do have a sequence of random numbers, which I do, if I could just look at pairs of those random numbers, determine whether they're co-prime or cofactor, look at the ratio of coprime to cofactor, solve for pi, then I could estimate the value of pi. Which begs the question, how do I determine if two integers are coprime or not? I've got some wonderful news for you. There's a well-known algorithm known as Euclid's algorithm to determine the greatest common divisor of two integers. And you can implement that algorithm with recursion. I can't wait to look at the YouTube retention stats of this part of the video. Unfortunately, something terrible has happened. I have to erase this so I can have some room to explain the algorithm. I'll provide links in the description where you can read up more on both the derivation of this probability as well as Euclid's algorithm or the Euclidean algorithm, but I'm going to try to describe it to you in my own words here in this video. The first thing I need to do is determine which number is larger. And for the sake of this moment, I'm just going to assume that A is greater than B. In my code, I can figure something out to determine which is the bigger number. I then need to take A divided by B and determine what the remainder is. I'll call that R. If, by the way, this remainder is 0, then those numbers are not coprime. If I take 15 divided by 3, I'm going to get 5, remainder 0. 15 and 3 are obviously not coprime because they both share the factor 3. Oh, I wasn't including the number itself in my earlier list of factors, which clearly I should have. If the remainder is 1, they're definitely coprime. Take the numbers 15 and 16 again. 16 divided by 15 is 1, remainder 1. Those two numbers are coprime. What if my numbers, however, are, say, 22 and 5? If I take 22 divided by 5, I get 4, remainder 2. As I'm moving through this, you're going to notice that I'm not bothering to write the 4 here. It's because this division actually doesn't matter. It's only the remainder that matters. And the term, the operator that you use in JavaScript for remainder of division is the percent sign. Is that modulo or modulus? Oh, the comments! I got it. The percent sign is the modulo operator. The 2, the result, is the modulus of 22 modulo 5. Will I remember this the next time I come to it in a video? Most definitely not. I should also mention that I'm kind of mixing things up here. I want to determine whether two numbers are coprime by calculating the greatest common divisor. And if the greatest common divisor is 1, then they are coprime. And so to be a bit more clear, if A modulo B is remainder 0, then that greatest common divisor is B itself. So this should say that the GCD, the greatest common divisor, is B. If it's not 0, I need to keep going. And the way that I keep going is by then taking B modulus that remainder. And I could call this R0 and then call this R1. And so, call this R0. B modulus R0 is R1. And I'm going to do this over and over continuously again. So now R0 modulus R1 equals R2. And I keep going and going and going. If ever this becomes 0, then whatever the value is here is the greatest common divisor. And by the way, if that remainder is ever 1, any number modulus 1 is going to be, I said it wrong, any number modulo 1. The modulus of any number and 1 will be 0. So in that case, the greatest common divisor will be that number 1. I wonder if looking at 2 example numbers will be helpful in explaining this, because boy, am I doing a terrible job. Let's try 93 and 10. 93 modulo 10 is 9 remainder 3. That's not 0, so keep going. 10 modulo 3 is 3 remainder 1. So that's not 0, keep going. 3 modulo 1 is 0. Hey, that's 0. This is now the greatest common divisor, 1. Guess what? 93 and 10, coprime. Let's change this to 95. 95 divided by 10 is 9, remainder 5. So 95 modulo 10 is 5. 10 modulo 5 is, oh, wait a second, 0. So guess what? The greatest common divisor is 5. These are cofactor, 95 and 10, not coprime. I feel ready. Do you feel ready? It's okay if you don't feel ready, but I feel ready to go and write this algorithm in the code now. Here I am in the P5 web editor. I'm going to write a new function. I'm going to call it GCD for greatest common divisor. I'm going to pass it two numbers, a and b. And I'm going to implement Euclid's algorithm in that function. The first thing that I want to do is figure out which is the bigger number. By the way, if the numbers are the same, they're not coprime, because a modulo a would be 0. And then the greatest common divisor would be itself. OK, got that. So first I just need to determine, is b greater than a? If b is greater than a, I just want to swap those numbers. I look forward to all your suggestions about how to handle this more elegantly, but this now is keeping both numbers, but always guaranteeing that a is greater than b. The first thing I want to do is calculate the modulus of a modulo b. I'm going to store that in a variable called r. If r is 0, return what? B. That's the greatest common divisor. Otherwise, what do I do? Well, now I want to check b modulo the remainder, but ultimately, what is that doing? That's checking the greatest common divisor of b comma r. This is where the recursion comes in. Return GCD of b comma r. Get rid of draw. Let's confirm that it's working correctly. What were the numbers that I tried? 93 and 10. And 95 and 10. So I should see in the console a greatest common divisor of 1 and of 5. It worked! It's very rare that I'll write something and it actually worked the first time. All right, a little birdie just said something to me in my ear, which is I forgot that this sort of fancy JavaScript destructuring thingamabobber allows you to swap two variables like this. Let's make sure it still works. Indeed it does. We're good to go. I guess if I really want to be sure that this works, I better also check 10, 93 and 10, 95. Phew, OK, I'm really good to go here. What's next? So I need my random numbers. I need those 100,000 pairs of random numbers between 1 and 100,000. And I want to get them from the book that I don't actually have with me, but that will somehow be appearing as if I'm holding it. Oh, look at that post-production effect there. Luckily for us, you can download all of the digits. I'll put a link in the description where you can get them yourselves. But I've already done that, and I've put them into a file called milliondigits.txt. It looks like this. It has that full sequence. And in P5, I can use the load strings function to get them. Little oddity about load strings, not that strange actually. It loads everything into an array. I just want the first element of that array, which has all million digits in it. And then I want to split those up into chunks of 5. All right, I'm looking through the string documentation to try to find a function that might work for me. Pad n, repeat, replace, slice. Yeah, all right. All right, maybe there's a better way to do this. I'm going to try using slice, which allows me to slice out a section of the string. So let me make an array called randoms for all of my random numbers. While I have some digits left, the number I want is a slice starting with index 0 up until, but not including, index 5. 0, 1, 2, 3, 4. That's 5 things. And then digits is just the rest of it. Strings are immutable, so this slice doesn't actually change the string digits. So I'm pulling the slice out, and then I'm slicing digits, the beginning part, off of the string digits. Add that number to the array, and if I've done everything correctly, I should have an array of 200,000 numbers. Perfect, 200,000. Now actually, those are not numbers. I've created little string slices, but I want to work with them as numbers if I'm going to be calculating the greatest common divisor. So let's add a parse int of num. And just to be sure, I'm going to take a look at that full array itself. You can see there is my random number sequence. Now, I think it would be fun to see, and fun is relative here, the estimation of the value pi converging as I go through that full list of numbers. So I'm going to make use of the P5 draw loop. And I need two values. I need the coprime total, or coprime count, and the total. That's going to allow me to compute that probability of any two numbers being coprime and then solve for an estimated value of pi. Just to sort of know that it's working, I'm going to add no loop to do draw just once this time. I'm going to have a global variable called index, which is keeping track of where I am in the random sequence. So A is random's index. B is the next number, random's index plus 1. And if A and B have a greatest common divisor of 1, increase the coprime count and always increase the total count. And let me just console log everything so I can see if this works. Ooh. I love P5 so much. It seems that you may have accidentally written randoms instead of random, just letting you know maybe you wanted to use random. No, I didn't. I wanted to use randoms, but I forgot to make randoms a global variable, and I probably shouldn't have called it randoms because it's very confusing, because randoms is very similar to random. So I really, really appreciate you, P5. Error message. I'm going to call it random sequence, make it a global variable, and try this one more time. Here are the two numbers I got, 10,097, 32,533. Their greatest common divisor is 1, therefore they are coprime. Dare I take out this no loop? I'm getting the same number over and over again. I forgot that I need to increase the index. So instead of increasing the index by 1, I'm taking them as pairs, so I'm going to go up by 2. And if index equals the end of that array, no loop, console.log, complete. Oh, look, I saw one that had 11. That was exciting. So it appears to be working. You know, I have to hope that all of my code and math is right, but I'm seeing all the numbers coming out in pairs. I'm seeing their greatest common divisor. I think I'm good. I'll wait just to see until it gets to the end so that I can see that it says complete, or if I get an error message. This seems to be taking an awfully long time. I'm doing this 100,000 times. 100,000 at 60 frames per second. I don't know, a lot of minutes. Oh, this is going to take a while. I'm not going to wait till the end. I'm going to hit stop now. I could do more than one per frame. We'll get to that. The next step, though, is that I need to figure out how to solve for pi. So this is now a variable in my system. The probability of the greatest common divisor of two integers a and b equaling 1 is 6 divided by pi squared. Let's say that this probability is x. And in my code, x is coprime count divided by total. So coprime count divided by total equals 6 over pi squared. And this is not pi squared, actually. It's my variable that I want to solve for. It's my pi estimate. I'll just call that PIE for pi estimate. I might just have pi for lunch today. And I could rewrite this thing to say pi squared equals 6 times the total divided by coprime count, or pi, the pi estimate, is the square root of all of this. I think I did that right. Let's add that into the code. Let pi, for pi estimate, square root of 6 times total divided by coprime count. Let's be really, really safe here and add some extra parentheses, although I don't think they're technically necessary. Let's get rid of this console log, and let's just watch console log pi. Oh, it's getting there. Come on, 3.1. Let's show me a 3.1. Yeah, 3.1. Can I get a 4? Can I get a 4? Let's actually draw this into the canvas. Whoop. Erasing the background might be nice. And here we go. Let's also make a little progress bar so we can see how things are going. I haven't tested this yet, but I'm just drawing a rectangle that's the full width of the window, and then drawing one that's the percentage along the way with a fill. Wow, this is really, really, really slow. Let's do more than one pair per frame. So that index increasing by 2 has got to be up here. Then I can do, let's try 5 per frame. And I should do this check here. So if I get to the end, no loop, complete, break out of the loop. And let's do 500 per frame. Ooh, maximum call stack size exceeded. Let's take a look at what A and B are. It really shouldn't, like, the numbers can't be so big that it can't possibly do the recursion to find the greatest common divisor. I'm going to console log them. Oh, look, there's a 0. Oh my goodness, of course. I said this earlier in the video. Let's think back to that time. I don't want to pick the number 0. You'll see why in a second. So my range will be between 1 and 100,000. The range has to be between 1 and 100,000. I can't use a 0 in this algorithm. You can't have a greatest common divisor with 0. So I can fix that by just saying +1 and +1. And now let's run it again. And there we go. Can I get a 4? Yes. Ah, look at this. There's my estimated value of pi with all 100,000 pairs of 5-digit numbers in the 1 million random digits book. I would encourage you to try it different ways. Certainly I could start from a different place in the book. I could look at every page of the book and see which page of the book has the closest approximation of pi. But I have another thought experiment I would like to try. What if instead of using those million random digits, what if I used the digits of pi itself? Here's a text file with the first 1 million digits of pi. Let's get rid of the 3 and the decimal place. Save that and upload it to my sketch. Now all I need to do is replace the file name from million digits to pi 1 million. And let me comment out this console log. I don't want to be doing that anymore. And there we go. I'm going to stop here. I'm very pleased with the fact that I have taken the digits of pi, divided them into groups of 5, found out whether those groups of 5s are coprime or not, and then used that ratio of coprime to not coprime to estimate the digits of pi itself. Thank you. Thank you. Acting. Thank you. I hope you enjoyed this Pi Day video. I feel like there's a lot of things that you could do to improve on what I've done. Certainly you could try to make the code more efficient, use more random numbers, pick your random numbers from some type of like a quantum thermodynamic machine that's true randomness. Is that a thing? I don't know. Also, I think there's some visualization possibilities. Is there a way to visualize the process of Euclid's algorithm? Looking on the Wikipedia page, you can see some nice diagrams there. That might be a starting point. I would love for you to make something. Please share it with me. There's a link in the video description to the Coding Train website where you can add your twist onto this coding challenge. And I will see you, well, I'll hopefully see you on this internet thing before next Pi Day. But I'll be back every year on the dot, March 14th. It's Pi Day. I'm going to go and have blueberry is my favorite kind of pie. Just putting that out there, and I'll see you later. I can't stop these videos. I got to get on the train. It was track 3.14228 apparently.
It's Pi Day. Delicious and sweet. It's the only number that you can eat. It's Pi Day. My favorite treat. Circumference divided by diameter.